Welcome back to the next video on the study of the Cartesian tensor calculus of Euclidean metric spaces. In this episode, we're going to go over the elements of tensor products. So, what are bilinear and multilinear maps? A bilinear map is a linear functional that takes elements of two vector spaces to provide an element of another vector space. So let's go ahead and propose a basic example of a bilinear map using a Euclidean space already introduced in a prior video. So the cross product of R3 with R3 maps to R3. This map expresses the operation of the cross product of three-dimensional Euclidean space. So a cross product of an element or set of this space yields a result in another space that in this case happens to exist in the same form. Another example of a bilinear map is yielded by matrix multiplication. So A of x and y and its product with A of y and z maps to A of x and z. So a bilinear map is just a simple example of a multilinear map. With more products, a multilinear map becomes more complicated. So if we have a product of three Euclidean vector spaces, say R3 with R3 and R3, mapping to R3, we have what's called a trilinear map, and this continues to generalize to higher dimensions. So what exactly is a tensor product? We have a basic understanding of multilinear maps, at least as much as we need to move forward in this series. So we're prepared to go ahead and define the tensor product itself. We'll consider two vector spaces, V and W, over the reals. Let's go ahead and look at a following bilinear map. So the product of the vector spaces V and W maps to the tensor product V tensor W. V tensor W, as I just mentioned, is called a tensor product. The tensor product of these two vector spaces is itself another vector space. If the direct sum of R3 with R2 stacks elements of Euclidean spaces in such a way that it provides a list of n plus m numbers, then the tensor product R3 tensor R2 is a stack of multiplication that provides a list of n by n numbers. And any element of tensor products are referred to as tensors. So real numbers are examples of tensors, where the tensor product operator is defined by the basic multiplication we learn in elementary school. So the tensor product of two real numbers is equal to the standard multiplication of those numbers. So the tensor product of two vectors generalizes to what's called the outer product of those vectors, and this moves on to matrix multiplication, so on and so forth. Now that we know what a tensor product is and that elements of these things are called tensors, we want to know what exactly is a tensor. So as stated before, we see that a tensor is an element of course, the tensor product, which is a vector space formed by a generalization of multiplication acting on other vector spaces that creates a stack of functorial products. However, we'd like to know more about tensors so that we can actually do something with them. If a tensor product is a sort of generalization of the multiplication operator within a vector space, then a tensor itself is just a generalization of the elements of a vector space. So a tensor expresses the relationship between objects of a vector space. To get a better sense of a tensor, we must not only consider what we know about vectors, which of course as we learned were elements of vector spaces in the prior video, but also the concept of dual vectors, which are elements of another vector space called a dual space. So let's go ahead and cover dual vectors and dual spaces. So if we have the field of real numbers, let's just say we have the field of the reals, then a dual vector is a linear functional similar to the definition of the tensor product, but in this case it just maps a vector to the field of real numbers. The combination of all dual vectors that can be extracted from a vector space yields another vector space called a dual space, which we just mentioned. Importantly, though, every vector space that can be imagined, such as V, has a dual space V star. The vectors existing in the original vector space are then called contravariant vectors with components denoted by upper indices. So x upper mu, x upper nu, x upper sigma, etc. Contravariant vectors can be represented as column vectors. For a 3-vector x upper mu, this can be expressed by the column vector ABC. So then, the dual vectors existing in the dual space are called covariant vectors, with components denoted by lower indices, such as x sub mu, x sub nu, x sub sigma, x sub lambda, etc. Covariant vectors can be represented by row vectors, and we know these transform differently than column vectors. So for a dual 3-vector x sub mu, this can be expressed as a row vector ABC. We have enough information, believe it or not, to formally define a tensor with more detail than we had before. And it just so turns out that a tensor of rank AB is simply a multilinear map from A dual vectors and B vectors to the reals. Because this multilinear map acts to preserve the geometric meaning of the quantities it represents, tensors themselves must be invariant under coordinate transformations. This means that objects that don't transform linearly cannot be tensors. So we'll come and look at traditional rank 2 tensors, which are common in the study of tensor calculus and differential geometry as a whole. Rank 0,2 tensors indicate 0 contravariant components and 2 covariant components, so then the indices of the tensor components are expressed by 2 lower indices. And for our actual tensor, we'll use capital T to know that we're talking about a tensor, and in this case we have lower indices mu and nu. This could be sub AB, it doesn't matter, we can use whatever symbol we want to represent the components so long as we know what we're talking about. This is a map, T, that maps the product of the 2 vector spaces to the reals. So this is just a bilinear map as a rank 2 tensor. Rank 2 0 tensors then are indicated by 2 contravariant components and 0 covariant components. So the indices of the tensor components are expressed by 2 upper indices. So we have T upper mu nu. This is a multilinear map that takes the product of the dual vector spaces and maps them to the reals. And so we only have one more type of rank 2 tensor, and that is a rank 1,1 tensor, indicating 1 contravariant component and of course 1 covariant component. So then the indices of the tensor components are expressed by 1 upper and 1 lower index. This is called a mixed tensor. And so we have T upper mu sub nu. This too is a bilinear map, but between the dual vector space with the vector space mapping to the reals. So rank 2 tensors are just matrices. Not all matrices are tensors, but all rank 2 tensors can be represented as matrices. Examples of rank 1 tensors are given by the following. There are 2 of them. We have, for one here, rank 0,1 tensors, indicated by 0 contravariant components and 1 covariant component. So then we just have a single index expressed by 1 lower index. So T sub mu. This is just a simple linear map that maps the vector space to the reals. This yields a dual vector, also called a 1 form. Rank 1 zero tensors then indicate one contravariant component and zero covariant components. So the index of the tensor component are expressed by one upper index. So T upper mu. This is then a linear map that brings the dual vector space to the reals. So this is just what we call a vector. And as we can see, rank 1 tensors in general are just vectors. Do rank 0 tensors exist? Well, we have the notion of a rank 0, 0 tensor in this case, indicating 0 contravariant components and 0 covariant components. So the indices of the tensor components are non-existent. So we just have a basic linear map that takes the real numbers and maps it to itself. But that's exactly what a scalar is. So this is a map from the reals to the reals, making a rank 0 tensor a scalar. We're going to get a little bit more advanced. We're going to look now at examples of rank 3 tensors. We won't have room to show all of them, but we'll show a few of them here. Rank 0, 3 tensors indicate 0 contravariant components and 3 covariant components. So the indices of the tensor components are expressed by all 3 lower indices. In this example, we have T sub sigma, mu, nu. This is a trilinear map that takes the product of 3 vector spaces and maps it to the reals. So rank 2, 1 tensors indicate 2 contravariant components and 1 covariant component. So the indices of the tensor components are based on a mixed tensor that's expressed by 2 upper indices and 1 lower index. So we have T upper mu nu sub sigma. This then is the trilinear map of 2 dual spaces, their product with a vector space mapped to the R's, or to the reals. So rank 3 tensors are 3-dimensional arrays, a slight of generalization of a matrix, basically. Finally, we'll look at examples of rank 4 tensors. We'll consider rank 4 tensors as they will be the highest dimensional tensor utilized within this series. Rank 2, 2 tensors indicate 2 contravariant and 2 covariant components, so the indices of the tensor components are expressed by 2 upper and 2 lower indices, as expected. So we have T upper sigma lambda sub mu nu. This is a map of the product of 2 dual spaces and 2 vector spaces mapped to the R's. Rank 1, 3 tensors indicate 1 contravariant component and 3 covariant components, so the indices of the tensor components are expressed by 1 upper index and 3 lower indices. So T upper sigma sub lambda mu nu. This is another rank 4 map here, but in this case we have 1 upper index, so we have a map of this tensor yielding 1 dual space with the product of 3 vector spaces mapped to the R's. And when I say to the R's, I mean the real numbers. So rank 4 tensors are 4-dimensional arrays. So hopefully we can see at this point that tensors are just generalizations of the elements of vector spaces themselves. Here's a decent little picture here from Dmitry Shulga showing the jump from matrix algebra to a tensor algebra. The general study we'll call tensor calculus. So we have a rank 0 tensor, which he calls a zero-way tensor, but these all mean the same thing. So we have zero-way tensors, one-way tensors, and two-way tensors represented by scalars, vectors, and matrices. And then we have the 3-dimensional arrays, 4-dimensional arrays for a rank 4 tensor, so on and so forth, up to some big N. So now let's just generalize this into tensors of higher rank. One might wonder what the highest ranked tensor is that a tensor itself can actually take. Like, what's the actual limit of the dimension? It turns out there isn't one, and so there is no highest ranked tensor. In physics, engineering, pure mathematics, etc., there exist tensors of exceptionally higher rank than the ones shown prior. I will go ahead and express an example of a tensor without a bounded rank. So we have the limit of t to the tensor power n as n approaches infinity. This is the following multilinear map between an infinite tensor product of vector spaces. And believe it or not, such a tensor may actually occur in physics, and especially in quantum theory, thermodynamics, string theory, and beyond. So we'll go ahead and leave this episode with a couple exercise problems, and all of these can be answered by taking in the information learned within this video exclusively. Number 1. Evaluate the rank of a tensor T upper sigma lambda phi sub mu nu in terms of a rank AB. 2. Express the multilinear map of a tensor T upper psi sub kappa tau. Number 3. Express all variations of a rank 4 tensor in terms of rank AB and tensor components using whichever letters you prefer. So it doesn't matter if you use mu, nu, a, b, psi, sigma, lambda, it doesn't matter. Number 4, maybe sort of a bonus, but it's actually a lot simpler than it looks. Evaluate the following. We have the star of the quantity v star. So we have the dual space of the dual space. What kind of space do you think that leads back to? Either way, I hope you enjoyed this video. If you have any questions, feel free, of course, as always, to reach out in the comments below. Thanks for watching.